Hi everybody. So today we are going to learn another lesson, and that is gases and ideal gas laws. So now, gas properties can also be modeled using math. So last week we kind of last 2 weeks we kind of just talked about, okay, what are these gases doing? What do they look like? What's going on with the particles, with the temperature and pressure and whatnot? Well, now we can model those behaviors using math. Now, this is very, very easy math. It's all it is plugging and chugging. I do a couple examples on this video for you. So these models depend on the following. They depend on pressure, so it'll be represented in a P, and the unit for pressure is going to be ATM. So whenever you see ATM, you're going to know that is pressure. And ATM stands for atmospheres. It also depends on volume. It's going to be represented by the letter V. And all the units for volume will be liters, the capital L. So whenever you see capital L or liters, you know that's volume. N is going to represent amount of gas, and that's moles. So whenever you see moles, that's N. And then we get capital T, which is temperature. Now, we all like to think that temperature is degrees Celsius, degrees Fahrenheit. Well, in chemistry, we're going to use capital K. Capital K is Kelvin. The way you're going to find Kelvin is you're just going to add 273 to whatever degrees Celsius you're given. Okay, just add 273. So this model is called the ideal gas law, and that equation is PV equals nRT. Pressure, volume, moles, R, and T. But what's R? We didn't talk about R over here. Well, R is always going to equal 0.0821. That is a gas constant. So whenever we're going to use ideal gas law, that is what R is always going to equal to. All right, so now here is a video of me doing two examples of these types of problems for you. All right, so we have two practice problems here. So we're going to do the first one together. It says a sample of a gas has a volume of 5.0 liters when at a temperature of 37 degrees Celsius and a pressure of 220 atm. Find the number of moles of gas. Well, we have the volume, which is 5.0 liters. We have the temperature at 37 degrees Celsius and a pressure of 220 atm. Now this problem is asking us to find the moles of the gas. So the equation that we're going to be using for this is our ideal gas law equation, which is PV equals nRT. So pressure is given in the problem, so we know that pressure equals the 220 atm. We're given our volume, which is 5.0 liters. We're not given our N. Our N, remember, is moles, so we know N is our question mark. Now remember, R is our gas constant, and R is always going to equal 0.0821. Then we get our temperature, which is given to us in Celsius. But remember, we don't want Celsius for our temperature, so all you're going to do is you're going to add 273. So when you take 37 plus 273, you get 310 Kelvin. So those are all our variables. So all you're going to do is you're going to plug it in to the equation. So we got our 200 220 for our pressure, timesing our 5.0, which is our volume. We don't know our N, so we're just going to rewrite N. We know our R. And we know our temperature. So now we need to figure out how we get N. And to do that, we got to divide this to both sides. So we have to take the 0.0821 times in the 310. We got to divide that to both sides. So that means this cancels because you're dividing itself. You get 1. So all you're going to do is you're going to multiply, and then divide. So you would get, let me calculate that real fast. So our N that we get is 43, and N is moles, so your unit is going to be moles. That is all you do. Make sure you have a number and unit. Don't leave your numbers naked. Okay? So let's go ahead and move on to our next problem. Now, our next problem says 1.6 moles of methane, CH4, has a pressure of 4.44 atmospheres at 250 degrees Celsius. Find the volume occupied by the gas. So we are given moles, the 1.6 moles. We're given pressure, 4.44. And we're given temperature. And our problem is asking us to find our volume. Again, the equation we're going to be using again always is going to be our ideal. So that's PV equals nRT. And we'll go ahead and start listing out our variables like we did in the last example. So P, our pressure, we know is 4.44 atm. That's just from the problem. Our volume, we want to find that, so we're going to do a question mark. We don't know our volume yet. Our N is given in the problem, which is 1.6 moles. And our R, remember, is our gas constant, so R is always going to equal 0.0821. Then we get our temperature, which is 250 degrees Celsius. But remember, we never want to use Celsius in these calculations, so we're just going to add 273. So when you do 250 plus 273, you get 523 Kelvin. So now we got all our variables listed out, so we're just going to go ahead and plug it in the equation. So our pressure, we said, was 4.44. Our volume, we don't know, so we're just going to rewrite V, equals our N, which is our 1.6. Our R, oh, I forgot to write that 1 at the end. Our R is that 0.0821. And our temperature is the 523. We got to get V, volume, by itself, so we're just going to divide 4.44 to both sides. Just basic algebra. So that cancels. So V would equal multiplying all these numbers divided by a 4.44. So we get 1 point. So let's see how that equals. And that will equal, so our volume equals 15 liters.
right? Volume always going to have a unit of liters. There you go. That is all you do.
Alrighty. So I will also post a picture of this sheet, and also link this video on YouTube for you to watch later as well. Alrighty, so let's moving on. So the use of ideal gas laws can be used to represent the relationship between variables. And with this idea, it helps us produce 4 gas laws. Our first gas law is Boyle's law, and Boyle's law is P1 times V1 equals P2 times V2. Now, 1 and 2, think of it before and then after. Before a reaction, something happened, then 2 is after the resulting. So you're going to have 2 pressures and 2 volumes. Now, this type of equation represents an inverse proportion. And what I mean by inverse proportion is if the pressure goes up, the volume goes down, or if the pressure goes down, the volume goes up. So think about oppositely. So with that idea, this Boyle's law graph kind of looks like a upside down exponential function, just like in a curve going down. So make sure you know the equation, inverse proportion, all of that, okay? Gas law number 2 is Charles' law. Charles' law equation is V1 divided by T1 equals V2 divided by T2. Again, 1 is before, 2 is after. Now, this law represents a direct proportion. And what I mean by direct proportion is if volume goes up, temperature goes up, or volume goes down, temperature goes down. And Charles' law equation looks like this. It's just a straight positive linear line. Gas law number 3 is Gay-Lussac's law. And Gay-Lussac's law equation is P1 divided by T1 equals P2 divided by T2. Again, 1 is before, 2 is after. And this also has a direct proportion. So if pressure goes up, temperature goes up, or if pressure goes down, temperature goes down. And this graph probably looks very similar to Charles' law because it is, again, a positive linear slope graph. Our last gas law is going to be Avogadro's law. Now, we've heard about Avogadro before, avocado, the 6.022 times 10 to the 23rd number. Now, he also has his own gas law as well, and that says that volume 1 divided by moles 1 equals volume 2 divided by moles 2. Again, 1 is before, 2 is after. And this again also represents a direct proportion. So as volume goes up, moles goes up, and as volume goes down, moles goes down. And again, the graph's going to look very similar to Charles and Gay-Lussac's law because it's again a positive slope linear graph. All right, so make sure you know the different types of gas laws, the equation, direct or inverse, the graph, and all that good stuff. All right, so that's it. That's all I have. So again, let me know if you have any questions.